Shall we begin? Is everyone ready? All right, welcome everyone. I'm Catherine Kuchenbecker. I'm a director at the Max Planck Institute for Intelligent Systems, and it's my pleasure to host today's distinguished lecture series on behalf of the ELLIS unit Stuttgart, which is a joint enterprise of the University of Stuttgart and the Stuttgart side of my institute. And it's really our significant pleasure to host Professor Jens Kober here today. I want to tell you a little bit of his background because he's actually an alum of the University of Stuttgart. He earned his, I think, a diploma in the Technische Kybernetik, so control engineering. He also has a degree in general engineering from Paris. And then after that, he did his doctoral research with Professor Jan Peters, who's now at TU Darmstadt, but at the time also had a connection with the Max Planck Institute for Intelligent Systems in Tübingen. So he's also an alum of our institute. And after finishing his doctoral degree, I believe in 2012, he won the George Girault PhD Thesis Prize, which is for the top thesis in robotics in all of Europe. It's really a very prestigious prize, and he went on to do postdoctoral research in Bielefeld, as well as at the Honda Research Institute of Germany, before beginning his faculty career at TU Delft, which is the top technical university in the Netherlands, which is not so far away from us here in Germany. And he's had really also an outstanding career there, winning many prizes. For example, I think RSS Early Career Talk Spotlight Prize a few years ago, and many other things. And so I'll stop embarrassing him. But I'm really glad you all showed up, though it's early in the morning. I have a few administrative points also before I hand over to Jens to give us his talk. We have a list here, and it would be great if you could write your name and sign so we can keep track. And also, if you want to ask questions, is it okay if people ask questions along the way or at the end?
Sure.
If and when we ask questions, we need to speak into this microphone so that it's recorded, because we share this online for other people to be able to benefit from that. All right, is there anything else that I missed? Anything we need to say? All right, then let's please join me in welcoming Professor Jens Kober, who will be telling us about robot learning through interactions.
Thanks a lot for the very kind introduction and also for the invitation. One additional thing to very briefly mention, I'm also part of ELLIS, the ELLIS unit in Delft. So it's also great to be connected in this way. And it really feels like coming home, as you can imagine. So as Catherine was saying, I'm going to talk about robots learning through interactions with the environment, like this bottle, but even more about interactions with a human teacher. You can see Anna, one of my PhD students, I placed her hands on the bottom right corner, giving some corrections, in this case, to the robot while it's doing its movement. Before I'm going to dive into the technical details, and I will probably have to skip a few things as usual. It's also depending on how many questions you ask throughout. I very briefly wanted to give you some high-level introduction thoughts. It's not going to be scientific. I don't claim I know that much about human learning, but at least for the type of robot learning we do, you often at least draw inspiration from how you see humans and other biological beings learn. What I'm interested in are something called motor skills. So that's movements on the order of a couple of seconds, maybe a minute. You could think about a forehand or a backhand in table tennis, a grasping motion or something like that. And for learning those in robotics, we take inspiration from how humans learn. So on the left, you see an image illustrating imitation learning, where the student, or the robot in our case, observes a teacher and then tries to mimic what it has seen. That tends to work fairly well for fairly simple and slow tasks, and for more complex tasks, you need to practice, so do reinforcement learning. Inspiration doesn't stop there. If you think about how a human child learns, it takes forever in the beginning until a baby can do a goal-oriented grasping task. It's doing lots of motor babbling and exploration, and then after a year or so it can do goal-oriented grasping. And from then on, it starts to really go very quickly. So what humans and animals tend to do is to build up some kind of a skill library of basic skills that you can reuse and adapt and then transfer to related tasks, like first flipping out the book before you grasp it. And in order to do this transfer, it's not only about observing and messing around, but we also use our brain. And for doing so, we have a notion of intuitive physics. So we know that an apple is going to fall, and then you can start in your brain, think about how things are going to play out, so do a form of mental rehearsal. And also those you see very much in robot learning, learning in simulation, doing a form of planning. Could be a very accurate model, could just be a crude model that gets you in the right ballpark to warm start the learning process. And what I really got interested in about 10 years ago or so is interactions with teachers. If you think back to the baby, it's going to interact constantly with caregivers who are going to provide encouragement, demonstrations, and so forth. And you have the same if you're learning a sport or learn to play a musical instrument. You can do it on your own, but usually it's a lot more efficient if you have a teacher or coach that tells you what to do, what to practice, what to focus on, what to improve, and so forth. So you have some form of continual, at least intermittent student-teacher interactions, where you get additional demonstrations, intermittent feedback, or other types of input. And you see that more and more in robot learning. I believe the benefits are that it really helps to speed up the learning process, which in turn then enables a robot to learn more complex tasks, and hopefully that's also intuitive for the human teacher. And that not only works for teaching our kids, but also for other biological entities like these two here. So far, some ideas on how to kind of connect ideas on how humans learn to how robots learn. Now let's look at some more concrete examples. I'm going to start with something that was actually my diploma thesis a long time ago. There we tried to learn ball in a cup. That was my cousin's daughter. She was around 10 years old back then. I took her 35 times to catch the ball in the cup. If I give it to an adult, it's more like 20-ish or so. And then we tried to mimic that with a robot. So what it looked like is we first provided a demonstration, and then if you just play that back, it kind of works, but still misses by a bit. And then if you do reinforcement learning, if I try to optimize roughly the distance between the ball and the cup, it takes some 30, 40 trials until it gets the ball in the cup sometimes, but usually it bounces off, and then after 100 or so, it has nicely converged. So same order of magnitude, and very, very really proud of that. Now the question is, can't we do better? And that's where the idea of interactive learning comes in. Before showing you, again, the ball in a cup example with interactive reinforcement learning, I'm going to very briefly introduce what I mean more specifically by interactive learning. So we're going to have an agent, a robot in this case, and the environment. We have a state, could be the position of the robot and objects in the world. The agent has a policy that, depending on the state, picks an action, and that is typically parameterized by some parameters theta in this case. The robot takes an action, and you get this loop, which you probably know from control or reinforcement learning. What we now have additionally is a teacher who literally stands in the center, and we assume that he or she can observe both the state and the actions the robot took. And then it's the teacher's task to once in a while provide some form of feedback. And there you can do a whole lot of different things on the spectrum, from just providing binary feedback, success, failure, which is hopefully fairly easy for the human teacher, but not that informative for the robot learner. And on the other end of the spectrum, you can do something very similar to imitation learning, where you assume that the teacher needs to give the perfect action for every state the robot is in, and where it did something different. What worked well for the kind of tasks we are considering is something in the middle, and what I also have on the slide, namely corrections, where the teacher provides a correction which is more like a gradient, so an offset in a certain direction, like move more to the left, move faster, move slower, but not necessarily the absolute amount you're supposed to move. So it's just pushing the robot in a certain direction. So how that looks like, if we take a little example, and many of the approaches I'm going to show you are also based on this method called coach, corrective advice communicated by humans, that my former postdoc Carlos Selemin came up with. It looks something like this. Let me see, do I have a pointer somewhere? Yes, that will work. So the robot car in this case is supposed to drive down the road on the right side of the road. It has some initial policy, which you see in red here, which kind of does the right thing, but not really. And then once in a while, the human teacher jumps in to provide corrections more to the left, more to the right. The robot is going to aggregate those, to take those into account, and then hopefully in the next iteration, it's already going to work better, and the human needs to jump in less frequently. What is also very helpful in our experience is if the robot directly reacts to the correction. So if you, for instance, press a button on the keyboard to indicate move more to the left, if the robot doesn't react and just kind of stores it in the memory and then use it for using it later on, that's very counterintuitive for human teachers. So, and then they tend to overcorrect or not correct enough. So if you can manage to have the robot directly react and then already move to the left in my example, that just tends to work a lot better. And then in the end, hopefully the robot can do the task autonomously after a couple of iterations. So what we could do now, if we take the same kind of template we had for the initial example I gave you, we replaced the human demonstration, which took a lot of human practice by Katerina, my colleague. We replaced it by this interactive correction approach. And then once we have something that roughly works, you could refine it using policy search or reinforcement learning. That works, but effectively you don't gain much. So what we wanted to do is to do everything in one combined loop. And how that looks like is that we modeled the exploration, which you have in reinforcement learning. So the robot trying out something, a random action, to see if that improves or the performance or makes it worse, by modeling the human teacher as a form of exploration. So either you have random perturbations or the teacher corrections. And that allows us to very naturally integrate it in a fairly standard policy search reinforcement learning approach. So that's how a standard policy search approach looks like in pseudocode. You have a current policy, you try that out, see how well it works, and then you do a couple of iterations. So that's the for loop here, where you have exploration. So you try some variations of the current policy, and then you calculate the cost for each of those, so see if your variations improved or made things worse, and then you update the policy parameters. Now, if you make that interactive, what we have additionally here is an if-else switch. So if the human starts to provide guidance or corrections, then we switch to using this coach method I introduced a few minutes ago, and otherwise you do random exploration. Why do we have this hard switch? Again, turns out if the robot tries random stuff while you're trying to correct, that, yes, exactly. You shake your head and you get extremely confused. So we have that switch here. One important thing to mention here is how it's set up here, because we simply evaluate the cost of each rollout, is a big assumption that the goals of the human and the robot are aligned, so that the human teacher is trying to optimize the same reward function in this case. If not, the robot is not going to benefit from the corrections, and if the teacher is constantly correcting, then the robot just won't learn anything at all. It looks something like this. Now we can actually start from scratch, so initialize the policy to 0. What you can't see is somebody sitting in front of the robot with a keyboard, in this case, providing corrections left, right, faster, slower. And then after some 20 trials or so, the robot can actually catch the ball in the cup. So now we're really as quick as a human learner typically. In a plot that looks something like that, so we have the number of rollouts, number of times the robot tried, and here the cost, so lower is better. PS is policy search, the reinforcement learning approach without human interactions, which is the same as in the original video. And the plot I'm showing now is also with an initial demonstration. So we warm started, and then it takes some, I don't know, 30, 40 trials or so until it reaches the cost where it tends to go in. For the pure imitation learning approach with human corrections, we are very quick with some 10 or so trials. However, at the end, we level off to something just because the human teacher can't manage to give as fine-grained feedback and corrections. And then if we combine that with reinforcement learning, that's the blue line here, we're almost as quick, and in the end, we get the best overall performance. Now, that's not very impressive yet. The picture changes completely if we really start from scratch, like I was showing you in the video. And then doing pure reinforcement learning takes some 200 or so trials before it can learn it, if you're lucky. While the interactive approaches are almost as quick as doing the warm start. That much on using interactions in reinforcement learning. The remainder of the talk is all going to be about imitation learning. So the idea that the robot imitates what it has seen, and then by definition, whatever the human teacher shows is the correct thing to do. So the robot is not on its own optimizing for its own criterion. So imitation learning is really not only about just playing back what you've seen and recorded, so picking up the bottle here, but it really is about also generalizing. So if you move the bottle to a different location, you don't want to play back that movement, but you want to move to, where the bottle is. And in order to distinguish whether the robot is supposed to move relative to the table or relative to the bottle, you could use two demonstrations, and then based on the statistics of it, you could distinguish that and generalize. Here's also a pretty old video from my time at Honda Research, where we tried to teach this flipping up of a box movement, and then you could grab it from the top because it's too wide to grab, for example. And here, really, the main goal was to figure out what the correct reference frames and control modalities are. Is it supposed to move relative to this supporting part here, to the box or to the table? Is it supposed to push down? Is it force controlled? Does it have some kind of cylindrical coordinate system, and so forth? And it very nicely generalizes to different positions of the box, the support, and even different sizes of the box with some 15 or so demonstrations. So we also did something very similar more recently. In the previous videos I was showing you, we had very simple movements, effectively straight point-to-point movements. And now we wanted to see if we can also have more complex shapes in the movement. Again, with a big focus on figuring out the task frames. So that's, for example, the initial demonstration. And then if you move the task frames or the objects around, then it's supposed to generalize to something like this. How our new method looks like is that, again, we have a set of initial demonstrations. We project them into all possible different task frames. So you take a look at the movement from the perspective of the bottle and the table and whichever other object you have. We align the different demonstrations using the long and comest subsequence because people tend to move at different speeds if they do the demonstrations. We train the local policies, so in the different reference frames using Gaussian processes in this case, and I'm going to tell you a bit more about that later in the talk. And then what we additionally have is a classifier that decides on when to switch to which of the different reference frames. And that allows us to, because now we have a lot more complex representation of the actual movement, we can do more complex things. So what it's doing now is actually, and that needs to be improved, just finding the markers and the object locations, and then doing the generalization to the different positions. So then you can move the target position around, in this case with the little marker. Okay. There we go. And it also works for the higher shelves and so forth. With both of these approaches, one of the big assumptions is that the demonstrations you provided are sufficiently rich to actually distinguish between the different reference frames or to resolve the ambiguities. So if you have a scenario like this, where you only provide demonstrations where this mug is on the coaster, there's no way the robot can figure out if it's supposed to move relative to the mug or to the coaster. But actually that only becomes relevant once you separate the two objects. If also when the robot is supposed to execute that, the two objects are always together, doesn't really matter. So here now our idea was to really make that interactive and not require the human teachers to beforehand think about all possible relevant combinations and provide demonstrations for that. We'll actually start collecting some of the demonstrations, train the system, test it out, figure out, oh, I forgot one configuration, let me provide an additional demonstration, retrain, and then you already have some kind of an interactive approach, but rather make it driven by the robot. So the robot is going to ask for additional information if it's uncertain on what to do, and if the different possibilities don't coincide. So it looks something like this. We already taught it how to do a pickup movement and to put it, oh, it's very dark, in this crate with cucumbers here, and that works for different initial positions of the cucumber. However, now if we swap the two crates with the apples and cucumbers, then it can do the first part of the movement autonomously, but then it didn't know if it's supposed to move relative to the crate or to the world coordinates. And then just with one little push, we can disambiguate that, and from now on, hopefully the robot is able to do that itself. We also ran a user study with that, comparing kinesthetic demonstrations. In this case, these boxes of tea needed to be stacked in a certain order. And then really the task of the participants was to provide all the demonstrations and to think about which combinations you really need to provide so that all the different combinations are covered. So yeah. And then we compared that to our approach called learning interactively to resolve ambiguities, where you provide just a single kinesthetic demonstration. And then the robot does as much as possible autonomously. And in this case, it was a screen-based interface where you can provide additional corrections in this case. So if we then ask the users to rate the two methods, so KT is the kinesthetic teaching versus Lyra, and you have this NASA TLX score here where lower is better. You can see that they really, really preferred the interactive approach. It's faster, and what they also said when we were discussing with them, it's also a lot less mentally demanding. You feel really guided, and it really also helps to understand what the robot knows and doesn't know and how it works. Okay, so that was more on the high level of figuring out what the correct sequence is or what the correct reference frames are. And I'm going to switch gears a little bit and talk about the representing and learning the actual movements. So if we want to also have raw camera inputs in there, we used a very traditional autoencoder structure where we have some kind of low dimensional latent representation on top of which the policy is learned. And traditionally, you would pre-train this latent representation, a compact state that you can use then, and then on top of that, learn the policy, and then either freeze the encoder or also fine-tune that by learning the policy. That works, but then you need to have access to some kind of data set that is representative to the task that the robot needs to do, which you need to collect beforehand. And also there we wanted to see if we can't do it all in one go. So learn the representation at the same time as the policy, and now the decoder serves more or less as a regularizer, as an auxiliary task to provide some additional information on how to structure this latent representation. And we can actually learn it at the same time. It's as quick, and actually the final performance is better. It's a bit different from what you would usually assume. And why it works is that effectively, in the beginning, the robot doesn't have a good policy anyhow. So effectively, if you're providing corrections, you're effectively teleoperating the robot anyhow in the beginning. And during that time, you can start to collect enough data to get a decent latent representation and decoder. And then once everything starts to work, that has learned sufficiently well. So here's a little video of that, the robot learning to drive on the right side of the road. On the top, you see the crappy camera image from the Stucky bot. On the bottom, that's the reconstruction of the latent space, which is actually comparatively bad, but we don't really care about the image quality as long as it contains all the information it needs to learn the policy, so the road boundaries or these kind of things. And then you can do instantaneous validation after some 10 minutes or so. Take off your hands, see how well the robot does. If you're happy, you're done. If not, you can continue providing corrections. In this case, it was really with the arrow keys on the laptop. There we had just a single image as an input that worked well enough for this driving at a constant speed. If you want to do something slightly more complex, either if we don't have full observations, for instance, of the velocity of objects from just a single camera image, or we need some other kind of memory, then we did the very obvious thing of including a memory unit, so an LSTM in this case, in the network. And what also changed is that now we are reconstructing not the observation directly, but of the next time step, so that forces it to learn the dynamics. And it looks something like this. What the robot can see is only this part in white here. So what you also see in the middle on the right. And then it really needs to memorize where these fake oranges are in order to then pick them up or point at them. And then after already 5 minutes or so, it can do pretty well. And then after 15, it has pretty much converged. And what's really cool is that if we already have a decent latent representation, we can generalize to a related new task. So in this case, it's supposed to avoid the pairs by moving up. And then you see Rodrigo using the keyboard again to provide corrections. And after already 3 minutes or so, it has adapted to this new task. There's many different ways in which you can provide feedback. So the things so far, you've seen keyboards. On the title slide, I had a game controller. We've used Space Mice and a whole lot of other devices. But still, the question is, in which space should you provide feedback? In the action space is very direct. However, it's also high dimensional. And if you have to, in your mind, do the inverse kinematics, that's rather non-intuitive. So the more natural choice often is to do it in state space of the end effector Cartesian coordinates or something like that. For that, you need an inverse model. If it's just the end effector, that's what the robot manufacturer provides. But you could also have other cases like this one here, where what you actually want to control is a bit more complex. So what we wanted to do here is to control the laser pointer on the space of the whiteboard, so provide the corrections really in the space X, Y of the whiteboard. And what we're learning here at the same time is the inverse kinematics and inverse dynamics at this and the actual task. And then after some 10 minutes or so, it can write the letters we want to teach on the whiteboard. And you can also, if you have a good representation of the inverse kinematics and dynamics, generalize that to more things. So far only free space movements, and with a single arm, things become a bit more interesting if we actually have 2 arms. And then here the question is, how do you teach that? Teaching 2 arms and moving those around kinesthetically is also rather demanding. So what we did here is to first teach them individually and then provide corrections to learn the synchronization between them. So here it's more or less symmetrical. We also did other things like handovers, where it's really about the timing and figuring out what should be synchronized and what is actually independent. The other tasks that you frequently see are ones where you have physical interactions with the environment, where you need to provide some forces, where you have friction and so forth. Also here, we wanted to start with kinesthetic demonstrations. If you can get away with that, that tends to be very intuitive for non-robotics experts to just grab the robot, move it around. However, if you have forces in there, that tends to mess up the dynamics, and you can't really do that nicely and record those nicely from a kinesthetic demonstration. So here it's going to be a two-step approach. First, provide kinesthetic demonstrations for the movement, and then interactive corrections for both the trajectory and, in this case, the stiffness value. So it's an impedance controller. So here, very classical whiteboard wiping task. Provide an initial demonstration. And if you just play that back, it doesn't know that it's supposed to push down or that the attractor or reference point is actually below the surface. So now Anna is going to push down here on the space mouse to indicate it's supposed to move lower, and it's going to adapt the trajectory and also the stiffness values you see on the top here. And then you can also directly see if that worked or not. In this case, with a single correction, that was sufficient for this task. So that looks something like this in the end. That's seen from the side, so the table is effectively coming out of the screen. And in the background, the color is the force that is applied. The red dots are the original trajectory, and then in black, the final corrected one. And what you see with these arrows is a attractor field represented by a Gaussian process that is effectively trying to minimize the uncertainty and pull back the movement towards where it has seen a demonstration. Which directly brings me to robustness and stability. So here the idea was to do a restocking task in a supermarket environment, and they told us that you need to get it down to 5 seconds or so to be anywhere close to realistic. So also here we provided an initial demonstration, and moving it that fast is just very difficult. So what we have now is the possibility to correct independently the trajectory and to speed up certain parts of it. And why is that under the heading of robustness? Because the timing of the gripper is extremely inaccurate. It's plus minus half a second for us. So there we really had to rely on the human ingenuity to come up with a trajectory that is robust to this variation in timing. And then here now in real time, the final movement that takes exactly 5 seconds in this case. We also did a user study there in a simplified setting. We can also generalize to having moving objects. And that's what I already showed you a little bit in a different setting. In this case, it's unplugging an electric plug, where really the idea is to get robustness by knowing what it doesn't know. So in the areas with the Gaussian process where you have demonstrations, you have a high certainty. For instance, down here, it's very uncertain. And what how we represent the policy is that it follows the gradient towards the more certain region. So it automatically pulls it back to the region where it's certain. And then, however, if you're too far away and it's totally uncertain, then you also get a flat gradient and just stops doing anything, which you just saw in this example where we tried to pull back the bottle. That's now kind of combining the human insights to gain robustness and stability, using the representation as well to get a notion of that, but we can also make that more formal. So already, if you see those vector fields, and if you have a background in mechanics, control, you think, okay, yeah, that's a dynamical system, and that's one of the common representations of these kind of movements. And there we could actually try to enforce asymptotic stability so that it really always converges to a certain goal, target location in this case. So effectively, how the dynamical system is represented is given the current state, you want to know what the next state is, so that corresponds to these little arrows I was showing you. So if we have, like we saw in the example with the ducky driving, a latent space and a neural network, we can actually use that to our advantage. And if we define a diffeomorphism so that there's one-to-one mapping between the task space and the latent space, if we can ensure stability here in the latent space so that it always converges to this center point in this case, then also the movement in the task space is guaranteed to always converge to that to its goal position. Here's a little example of that. If we just do imitation learning, behavioral cloning, it's way too dark. So for example, here you can't really see it on the screen, I'm afraid. It's diverging and going in this way. Also here it's going out of the area and so forth. So if you don't do anything additional, you just throw all the data in a neural network and optimize it to imitate the movement as well as possible, you get these divergence, you get spurious attractors, and you get limit cycles, which is usually fine if you stay very close to these red lines, which are the demonstrations, but as soon as you move away, then often all bets are off. So that's illustrated here. In the red region, that's where you have some problematic behavior. If we now enforce the stability in the latent space, in this case, it's a form of a PD controller that is pulling it to the center, then you can see that it's nicely globally stable for the space. And then with an example here on a robot, so we provide a few demonstrations, and then it nicely works for different initial conditions. And I think here also, if you disturb it, again, it's going to be robust to that. So far, lots of bits and pieces. The final 2 or 3 things I wanted to show you is some ideas on putting it all together. But to be honest, it's still quite far from really putting all together and making it a complete system that would be deployable in a household or in a factory. I already showed you quite a few different ways of providing interactions, ranging from keyboards, space mouse, game controllers, kinesthetic demonstrations. But it gets even worse than that. You also need to think about whether it should be driven by the human teacher, which were the latter parts of the talk, or it should be really the agent or the robot that is asking explicitly for help, like we had with this cucumber placing task. For the human teacher, you can roughly think about providing corrections in the action space or something in the reinforcement learning space, whether it's good or bad. And then also the robot can have different types of uncertainties. It can be epistemic, so it doesn't know what to do just because it hasn't seen any demonstrations or data yet. Or it can be aleatoric, which has actually contradictory information or contradictory demonstrations and hence is confused about what to do. We now, in this paper, we tried to put it all together, so to enable all these different modalities and interactions in one big framework. Effectively, it's mapping everything back to corrections in actions. And it looks something like this. It's a little, kind of like an air hockey task, where the robot is supposed to stop that little cart. And the human teacher can provide corrections and feedback, and the robot can also ask if it's uncertain. And here, that's the final movement, the final policy, where it does quite well, at least in the middle of the range. So yes, it's possible to combine all those. That works well if you mock up the teacher and learn it on some simulated typical benchmarks. It also works fairly well if you're the first author of the paper and you've played around with it a lot. But again, if you ask different users, even if they come from a computer science background, it very quickly becomes very overwhelming and they start to just pick one of the modalities and try to get as far as possible with that. So that clearly indicates that there's still a lot to be gained on the side of the user interface and user interaction. Here's another example of putting things together in a slightly different context. That's from a series of competitions we participated in, where the task is to solve these task boxes. So again, we start with a demonstration, and then we do a few rounds of corrections to fine-tune it. Additionally, it has some failure recovery behaviors in there. And some visual servoing. So if it's, you can see it starts to spiral to get it in to be a bit more robust to perception inaccuracies. And then also it has effectively a finite state machine on the higher level that defines in which order to execute the task. So here, that's a little part of the complete run where you need to unplug stuff and replug and put the probe on some points and so forth. One of the more tricky bits was getting the probe into this hole, and you can kind of see there's like a second ring around it. So if you get stuck in this outer ring with the tip, then obviously it doesn't work any longer. So there you really need to be smart about the recovery. And we thought initially that this wrapping the cable would be very difficult. It's a deformable object, very hard to observe. But then kind of using, again, the intuition of the human teacher to do a sliding movement and actually use the physics and the environment to our advantage, then that actually was fairly simple. And this is from a couple of months ago, another iteration of the competition where the main thing was to solve a new task, which they hadn't seen before. So they just got this box like an hour before. They had to show it, and then within an hour they had to do all the training and teaching and adaptations. And our team actually won. So it was very cool to see that having this way of very quickly teaching and refining things can actually solve interesting tasks. So to sum up, I talked about quite a few different things. I guess the common thread is teaching through interactions. And I hope I could convince you that it's a very promising approach to speed up robot learning. It really plays to the complementary strengths and weaknesses of a human teacher. So if you, for example, think about the top right example with the ball in a cup, a human teacher is typically very good at providing the high-level intuition and getting the robot in the right ballpark, but then isn't very good at being very precise and very reproducible, and that's where the robot shines. The other cool thing is you can combine these ideas with many other methods. With initial demonstrations, you could combine it with learning in simulation first and then refining it on the real robot. One of the things we're currently looking into is using these generalist foundation models for robot movements kind of as a starting point, and then only using these kind of things to fine-tune and adapt it. If you want to know more, we wrote a ginormous survey paper on interactive imitation learning. Might be a good starting point, but it's like not 2 years old now, but actually it has picked up quite a bit also in the robot learning community since then. Like I was already saying, one of the big questions that is still open for me is how do humans like to teach and how should we structure these interactions? And for that, I strongly believe that we really need an interdisciplinary approach, not only us coming from the more technical and machine learning and robotics side, but we also need people from industrial design, psychology, workplace environments, industrial design, ethics, and so forth. So, what I was showing you in this talk were really, if you want to be mean, ways of helping the robot to learn quickly and to get it unstuck. But that's obviously not the real goal. My goal really is to enable us to teach robots very efficiently and quickly, adapt them to our needs, so they can then help us in the slightly longer run. With that, thanks a lot for listening. Can see the large part of my group and some other collaborators there, and on the right some of the agencies that provided funding for the cool stuff I was allowed to do. Thank you.
Thank you so much, Jens, for this great talk. What questions do you all have for our speaker? Matthias, please. We have a microphone for you, just so we can record it.
Okay. Yeah, so kind of like from a machine learning point of view, a bit of a low-level question. So thanks first for the really nice presentation. How do you combine, so you know, your talk was a lot about combining reinforcement learning and imitation learning, which is in my mind a form of supervised learning.
Correct.
So, and you have then two different losses typically, right? And my question is, how do you manage to get the right weighting between those two, right? Because I can imagine if you have a human user interact, you want to weigh this a lot higher, yeah, in kind of terms of updating the model than if you actually use reinforcement learning. So is this something that is, I don't know, yes, I'm just a machine learning person, so is this something that you tune by hand, or, yeah, so how do you do this in practice?
Yeah, excellent question. That's indeed a big open issue, I'm afraid. So the example I showed you with the ball in a cup, there, how it was set up, like I was already trying to explain, is that effectively all the weight was on the reinforcement learning loss, and then the human data was seen as any other kind of data, and kind of, if we're lucky, then it actually helps the reinforcement learning approach, because it also optimizes for that loss effectively. That comes with the obvious downside that that's probably, or maybe not, what the human teacher wants. What we try to do there as well to get around that is to additionally have inverse reinforcement learning in the loop, so to at the same time try to infer the optimization criterion for the reinforcement learning part from the human demonstrations, and then you can get some weird dynamics and complex loops if you're unlucky. So it helps, but it's also not the final solution. You could also set it up in a different way, which was we did in this final example I was showing you with the little catching the little car thingy example, where the main weight was on the human demonstrations and corrections, and then kind of the reinforcement learning or reinforcement feedback to kind of the opposite role. But even more generally, unfortunately, it's even more complex, especially if you're doing it iteratively, because it's very hard to tell if what the human did in the beginning is still relevant or not, because you might change over time. You might figure out, okay, the strategy doesn't work, so I need to change my strategy. And in other cases, maybe because you only visited that part of a state space in the beginning, you actually want to memorize all that. So it gets very complex very quickly, and yeah, it's kind of as transfer learning, where it's very hard to predict whether you're going to have positive transfer or negative transfer in a sense. So yeah, that's very interesting and a very tough and open question.
Good, more research is needed. What questions, other questions do we have? I'll take it to Andreas and then Iris. I saw you first.
Yeah, thanks for the talk. So just to clarify, so from my perspective, when I understand this correctly, the feedback that a human gives is always assumed to be accurate and correct, right?
For the reinforcement learning, the ball in the cup thing, no. For the rest, yes.
Okay, so because in reality, I think that's a pretty strong assumption, that humans always know best how to move and what to do. So I was just wondering, is there research in this direction as well? Kind of, I mean, at the lowest level, maybe to see the human input as, associated with some uncertainty at
Yeah.
least, but maybe even in the sense of, maybe not always trusting this input, but really on the robot side, kind of, being a bit more confident in the sense, or self confident to say, I get feedback from the human, but I don't treat it as, God has spoken, and I just follow what the human tells me. But
Yeah, indeed. Excellent question. And sorry, no, this one. So typically, what you would assume is that the human input has some noise on top of it, and you can model that and estimate that. So it's not, but then kind of that in the mean you have the correct and optimal behavior. And then you can use that, like you see in these top two rows here, that if you have already accumulated some evidence from the human and then you get something contradictory, then indeed you can catch that and treat that differently. What in practice also happens, which is important to realize, is that typically when you start out, the corrections or input the human teacher gives is not optimal, but rather you very quickly figure out, okay, that doesn't work, and then the human teacher also learns at the same time and adapts. And the final thing that is important to notice is that many of the things I've been showing you here, kind of the mindset is good enough. So we aim for something where the robot can do the task as good enough and quick enough, and is more important than getting the last 1%.
Mm-hmm. Yeah, just a quick follow-up, because you already mentioned this would have been my next question, because you said also the human adapts to the robot, so it's a mutual adaptive process, and to me it sounds like we need some more sophisticated user behavior modeling in a sense, right? I mean, I think you mentioned this, kind of observing multiple time steps and not just considering always one user input, but kind of all the history potentially, even like more like a dialogue setting, even like an NLP. People talk about dialogue. I think it's in the same here in a way, right? So you have a dialogue of humans giving feedback and input, the robots reacting to it, the humans figuring out, well, maybe this was not good enough or not clear enough in terms of feedback, adapting as well. And then you have this kind of mutual adaptation process, which I could imagine is quite challenging to model and deal with.
Indeed. So this one and a few other things we've done more in very simplified simulation settings kind of have first tiny baby steps in that direction of indeed modeling the various distributions and uncertainties on the robot side and on the human side, and using that to guide the interactions in some form of a dialogue, but indeed pushing that to the next step and really making it a proper dialogue. And I think indeed whatever LLMs in these kind of models could definitely help there to make this interaction even more natural. Would be extremely interesting. Yes. Yes.
Yeah, thanks for your talk. I was very interested in this example you showed, speeding up stocking shelves in a supermarket.
Mm-hmm.
And I was wondering, it was very impressive to see that you could get down to doing it so fast. But I was wondering if you have any mechanisms in place that you don't overfit to just one trajectory being executed really fast, but to still keep this general capabilities of picking up this carton of milk on different locations on the table and putting it in the shelf in different locations, or if it then is really overfitting to just being really fast in one trajectory.
That's unfortunately always going to be a trade-off. On the one hand, between how well it performs and to how well it generalizes. And then the other trade-off you have is how quickly you can teach it versus how general it is. The more narrow it is and the more overfitting indeed, the quicker you can fine-tune and teach it. So concretely, for these kind of tasks, we did a very classical thing of not only having the one initial position and goal position, but then a few combinations of initial positions and goal positions to hope to prevent at least partially that it's overfitting to those.
So I'm thinking about like a human practicing playing the piano or something, and they are playing a song and they get to one part where they continually make a mistake, and then they like slow that down and practice that very slowly until they can get faster and faster. Is that something that fits into this, into your framework at all? Like, is that a teaching moment, or is that a self-teaching moment? Is that just motor skills?
It definitely fits in the broader picture. We've been thinking about it quite a bit. So one of the things we're playing around with is some of the tasks, if they're highly dynamic, they're actually too fast that you can provide corrections and feedback. Then if it's really dynamic, then you can slow down the world. So maybe using a simulation to slow it down and get some feedback and learn in there is a good option. And that works. Explicitly figuring out when to slow down, that's a very interesting question. That you could say give the user the option to slow down again, but then again, user mental overload probably. And yes, I think you could do it both as a self-learning moment if you somehow have the possibility to detect that this part of the movement is always tricky, but then you get into the big kind of credit assignment problem, which actually is a nasty problem of its own, to figure out kind of where the cause for failure sits in a sense. But yeah, would be very cool to do.
I'm just because I'm curious. Are people looking into using a large language model to provide instructions for robots?
Yes. Yeah.
How well do they do? Do you happen to know?
So there again, you can do lots of different things on many different levels, as long as you stay kind of on the level of providing corrections or interactions on no, don't move towards this object but the other, kind of the stepwise things. There an LLM is very good. For the more low-level things, there's big initiatives that are trying to come up with these generalist vision language models for robots, vision language action models to be correct. There I haven't seen any direct papers yet on using corrections, but there's like 10 papers coming out every day, so I'm not sure, maybe. And what I'm really, really interested in myself, and what we've now started doing with a master student, is to, rather than using a keyboard or mouse, to use kind of language instructions. And then the big question is, okay, how do you map that to the more low-level movement?
Yeah, that's kind of the background of my question, because I mean, keyboard and mouse is good, right, for many cases, but in other cases you might want to use language feedback, like, and that's why I was also wondering if there are some efforts in this.
Yep.
In this direction.
Yeah, definitely. I think it's really task dependent. Also, if you think about again how humans would teach you a new task. Some things, yes, a language instruction or reading a book or whatever is perfectly fine. For more physical, the highly dynamic sports-like tasks, other modalities might be better.
Thanks.
I could ask a question, or someone else, if we have here, Konstantin.
Yeah, thank you. Thanks for your talk. I would have one question about, also maybe echoing Andreas' questions, about when users have maybe conflicting preferences about what should be done or how it should be done. For instance, imagine like a box stacking task, but one user only wants the box to go on the left other box and the other one only wants it to go to the right. So how would you integrate this kind of like user preference modeling kind of stuff into your framework, potentially for like doing things in a supermarket or whatever?
Yeah. Yeah, excellent question. So the obvious thing is you kind of take the user identity ID as an additional input and then condition it on that. Hopefully you should be able to learn maybe a few clusters of different preferences, and then once you kind of detect, oh, this new user corrects me in that direction, to then again transfer and pull that from the clusters you already have and reuse that. The nice thing about the approaches I've been showing you here is that they're really so quick that you can effectively also almost afford to learn an individualized scale policy per user.
Maybe I'll ask my question now. Thank you for the beautiful talk. Many of the questions have also touched on things I wanted to ask about, but a high-level question of how a human gives you demonstrations for your robot. You're using kinesthetic teaching a lot, where the person is directly touching and moving the robot. Did you ever think of doing more traditional teleoperation, like even motion capture based, where I could like control all degrees of freedom? What are the benefits and drawbacks? Why have you done so much kinesthetic teaching?
Yeah. Yes, indeed. We've also tried with motion capture and teleoperation. It really depends on the task. And the obvious advantage of doing kinesthetic demonstrations is you don't need any additional devices, very quick to set up, and you just go and do it. What we figured out works well is, or not so well, is if you do motion capture kind of without having the robot move, because then you have the big kind of embodiment transfer problem. But using motion capture to teleoperate effectively, that works well with the delays and whatever.
Yeah, you want to close the loop. I was wondering if the haptic feedback, like the robot feeling the constraints of the object or the surface or the whatever it's touching, the kinesthetic teaching, the human can kind of feel through the robot and be right there.
And then if you would do teleoperation, then you indeed would want to have haptic feedback.
Yeah, okay. What other questions do people have? Okay, perhaps that's a good spot to end then. Let's again thank our speaker. Thank you so much for this beautiful talk. And I encourage everyone to make sure you sign the list, and please come chat with the speaker and take a snack and chat with each other. So have a wonderful rest of your day.